Let's get started. So let's talk about async await and all these new concurrency features. So just a short introduction. Hi, my name's Cameron. A couple things about me. I first really love burritos, and as a consequence, I also work at Chipotle. Second thing is I love climbing mountains. That's why I live here in Colorado, and I also make a mountaineering app called Landscape. So I also just want to prepare you for something today. And all of our code examples, well, they're all cow themed. So Shane, you'll get it here soon. So yeah, I want to prepare you for some really bad bovine humor. Just be warned. Now you may be asking why cows? Well, cows are really great because they're never in a hurry, and we can demonstrate asynchrony. And also, when you have a lot of cows, you can pretty easily demonstrate concurrency as well. And finally, it's early in the morning and you might be falling asleep. This is an emoji-rich environment, so if these new concurrency features don't keep you around, then maybe the emoji will. So let's look at the example we're going to be modeling out today. We're going to take our collection of cows here, our herd, and each is going to get a bath, get some food, and we're going to collect some milk. And at the end, we're going to have a bunch of milk and really happy cows. And our goal when building this is to do so in a really performative way using these new concurrency features. So let's start with async and await. And on our journey with async and await, let's look at the programming paradigms we've used in the past to handle asynchrony. The first of which being completion handlers. Now, completion handlers are nice in that they're really simple and easy to set up, right? But they can be error prone. If you forget to call your completion handler somewhere down the line in your application, something's going to get messed up, right? And finally, they're hard to scale. When you try and chain completion handlers together for a while, you'll meet the inevitable pyramid of doom, which I'm sure you're all familiar with. And then there are promises. Now, promises are nice in that you can chain and transform values and keep away from this pyramid of doom, but promises also have the issue of poor local reasoning. The lifetime of a promise can far exceed the scope in which it was created. So that's kind of something for you as the developer to hold on to mentally there. So in Swift 5.5, we can express asynchronous intent using async and await. Here we mark our function as async, and now we can do any asynchronous work necessary, like in this example, network requests. An async function can be suspended partway through when waiting for things like, say, a server response. When an async function, when calling an async function, we need to use await to acknowledge that there's a possibility that that function may suspend. And here in this example, we're making 4 asynchronous calls to care for our cow, and via function suspension, they actually happen sequentially. Now, if the ergonomics of async and await kind of feel familiar, that's because they're closely modeled after the error handling pattern that we have in Swift. So when you have a throwing function, you always have to use try to acknowledge that there's a possibility that the function could throw an error, right? And that behavior is even enforced by the compiler. So async and await, it's the same pattern there. And also a fun fact, async and throws are actually composable. An async function can also throw errors. Now that might seem like kind of an odd use case, but it is immensely powerful. So just to illustrate how cool the async throwing functions are, let's look back at completion handlers for the same thing. You're probably familiar with this type of error handling using result, right? We can clearly communicate the success and error scenarios of calling an async function with these success and failure cases. But without using Swift's built-in error handling mechanism, we're having to peek into and explicitly pass around successful return values and errors. And also, unfortunately, we're doubling our pace to that inevitable pyramid of doom. So let's compare these examples side by side. We have the completion handlers with result from the previous slide, and the same thing with async await and try catch. We'll do try catch. You can see it's obviously much easier to reason about, right? We have one happy path and one error path. we're actually making double the number of asynchronous calls, but our logical branches are reduced significantly. So some of you may already be familiar with this async and await pattern from other languages. I know my first foray was using JavaScript. But Swift's version, it's built different, but in a really good way. So other languages, when you call an async function, it actually returns to you with some future or promise or something to hold on to synchronously. If we look at the return type of this function, you can see there's no future or promise that's wrapping this cow type, right? We just have cow. So async functions in Swift, they don't return anything to us synchronously. Like I said earlier, async functions can suspend execution while they're waiting for something. So when an async function suspends, it quite literally pauses execution, and there's nothing to handle synchronously when calling an async function because it quite literally hasn't returned yet. It's also worth noting that when an async function suspends, it's non-blocking. So other work is still able to be done in its place while it's waiting for resources. And if we look through the execution of this code here, we'll start at checkpoint A, move down to our fetch cow call. That could suspend, it could take a long time. And only once that's finished and it returns, we have cow, and we can move on to checkpoint B, in which we can use that cow. So in all the examples leading up to now, we've only used async on functions, but functions aren't the only thing that can be marked as async. In fact, property getters and initializers can also be async. So we can really just async all the things, right? So let's move on to another feature of Swift 5.5, structured concurrency. So structured concurrency, it's a programming paradigm, right? And it's analogous to structured programming, something that we already use today. So every if and else, every loop, every function, these are examples of structured programming. They literally give structure to our program, right? So structured concurrency is just structured programming, but with an understanding of concurrency. So the obvious question you should be asking is, what does this mean for you writing Swift apps, right? Well, you can now write concurrent and asynchronous code that looks and feels normal, just like normal synchronous procedural code. And this all starts with async let. So earlier when we were calling a function with await, we'd have to wait, of course, until that function returns to us, and then we'll proceed forward. Here, when we prefix with async, we can allow our functions to run in parallel with the code around it. In our example of wash cow, feed cow, and collect milk, they're not dependent on each other to move forward, right? They're interdependent, and, well, yeah, we can allow them to run in parallel. So at some point, we'll need the result of one of these, whether it be is clean, is full, or milk here. And when we need to use them, we have to use await. And await here is just an acknowledgement that that function may not have returned yet. And our function here that needs to use it will need to suspend until it arrives. Also note that when we call one of these functions, these async functions that can throw, we need use try, right, to acknowledge that an error could be thrown. And we use this when we await the value. That's just where we'd observe that happening. So this parallel and asynchronous code, it's all made possible via this new foundational unit called a task. Task can be thought of as a logical thread of execution. And it's very important, it's a logical thread. It's separate from an OS thread. These tasks always run in the background, and like I said, they support asynchrony. They can be running, suspended, or canceled. And in fact, all the async work that we've done in the previous examples have all happened within a task. And tasks, they're allowed to run in parallel when the system deems it safe and efficient to do so. And finally, tasks are non-atomic. They can start on one OS thread, suspend, and later resume on an entirely different OS thread. And for us, it shouldn't really matter. So let's look back and relate this async let and task together. When calling a function with async let, we're implicitly creating a child task for that function to run in. as we can see in this example, we're creating 3 child tasks with our 3 function calls with async let. So let's demonstrate how that might run. So we have 2 threads here, and on thread 1, wash cow starts, leaving thread 2 open to do some other work. Now in thread 1, wash cow suspends, and other work is able to be done. After a little while, wash cow is ready to resume, and there's some space open on thread 2, so it jumps over there and suspends yet again, allowing other work to be done. And sometime after it suspends, it finally gets the resources that it needs, and thread 1 is open, so it jumps over there and even completes. So in passing, I mentioned that async let creates a child task for that function to run in, right? So yes, tasks compose as a tree. A task can have multiple children, and those tasks can have multiple children, and there's a descendant tree there, right? So when a child task is created, it inherits a lot of the properties of its parent task. For example, like the priority in which that task is scheduled. Child tasks, they cannot exist longer than their parent task is around, okay? So this has kind of significant implications for one, task completion and also cancellation. And let's look at completion first. So we'll start with our function here, care for cow, and you may recall we have 3 child tasks that spin off. And a couple of them complete relatively quickly. But if we look inside of the collect milk function, we'd see that it itself spins off a couple child tasks. Now, only once both of those are complete can the task in which collect milk is running also complete. And now that all 3 of those child tasks are complete, care for cow, that task can complete as well. So let's relate all this back to structured concurrency. Remember, it's just structured programming, but with an understanding of concurrency, right? Async let variable binding and task lifetime are closely tied together. In Swift, as we all know, we enjoy static scoping. So that variable there, is clean, would not be accessible outside this function. So the task in which wash cow runs, it has no reason to run longer than is clean would be in scope. In fact, if is clean goes out of scope and the task in which wash cow is running in, if is clean goes out of scope and the task in which wash cow is running in is not complete yet, it is implicitly canceled and then awaited before exiting the scope. Now that might seem kind of odd. Why is it canceled and then awaited before exiting? But we'll make clear the cancellation semantics in just a moment. But this is great news for the ergonomics of structured concurrency. We can easily make sense of the lifetime of the task because they already follow the ingrained static scoping we've come to know and love. So yes, let's move on to task cancellation. So when needed, a task can be canceled to, prevent unnecessary background processing. When a task is canceled, its entire subtree, its descendant tree, is canceled as well. And while you may expect that when a task is canceled, it halts execution immediately, right? But that's actually not the case. Task cancellation is handled cooperatively. Each task down that descendant tree must do its part to observe the cancellation to make it take effect, really. And doing task cancellation cooperatively gives opportunity for any cleanup necessary. So, for example, maybe a background task has an open WebSocket, and just stopping execution immediately would be, incorrect, would cause problems because we didn't have a chance to close that WebSocket there. So, exiting from a function like this is exiting from a canceled task is often the best way to do it by throwing an error, and we can do this in 2 different ways here. So the first is we can use this task.check cancellation method. And if the task has been canceled, it will throw an error and we'll escape here. but if the task has not been canceled, it's effectively a no-op. We can also check for cancellation using this task.isCanceled property. And going this route gives us the opportunity to do any cleanup. And I found that I like to check for cancellation in checkpoints. And it allows for grouping up operations that may require the same cleanup steps. And you can see this at checkpoint 3. So we have a rule here in our cow universe in which when you go to wash a cow, you can't just leave the poor thing sudsy or damp. So that's why we don't check for cancellation after checkpoint 3, because the cleanup steps would be exactly these. If we get to this point, we might as well just continue through. So while async let is great for kicking off a known quantity of child tasks, it doesn't work well for us when we have an unknown quantity. That's to say, you don't know statically, you can't just look at how many child tasks you need to create. So in come a task group. Task groups provide a dynamic amount of concurrency. And it's especially great when you need to do any fetching of maybe a list of images, you need to process a list of files, or definitely anything list-based. Just go ahead and reach straight for a task group. Task groups come in 2 flavors, a throwing and a non-throwing variant, depending on your use case. Let's look a little bit closer at the ergonomics here of using a task group. So we're creating this task group using this withThrowing task group function, and it takes in a few parameters. The first here being the return type of the child task. The second being the return type of the group itself. Notice here that the first parameter being just milk, all of our child tasks have to return milk. If you have a heterogeneous list of things that need to be fetched, I'd recommend making an enumeration with associated types. But in this example, we're always returning milk from all these child tasks. In this example, the return type of our child task and the task group itself, they're the same just because milk is combinable here. But anyway, let's move on to creating a task and adding it to the task group, which can be done with this group.addTask method. When tasks are added to the group like this, they can start executing immediately, and they can go in any order. And later, when we actually need to collect the results here, we use the group, which is actually an async sequence. We don't have time to really get into async sequences today, but they're super cool. The promise of an async sequence is you can await on values that may not have arrived yet in your sequence. So what we're able to effectively do is stream the results of our tasks as they complete and handle them right here. So the task tree here is very easy to visualize. We're creating a dynamic number of child task in which care for cow is running. And if you recall the implementation of care for cow, and we could just peek into there real quick, we spin off 3 child tasks a piece in there. So you can really get a sense of the concurrent nature of your program just by clicking around a little bit and just seeing things happen. It's much, much easier. So let's do a little bit of wrap up on structured concurrency before we move on. We can create a known number of child tasks to run in parallel using async let. With the task group, we can create a list of child tasks that can also run in parallel. Tasks cannot outlive the lifetime of their parent task, and we can easily make sense of concurrency locally because of the static scoping semantics that we can use here as well. So while Swift does provide structured concurrency, there is unstructured concurrency when you need it. That is to say, the language isn't handling concurrency for you anymore. You're on the hook for it, right? So we can create tasks that don't have a parent. And really, I guess, you as the developer, you're the parent kind of because you're having to manage it. You get way more flexibility because you're managing the lifetime of that task, but you also have to manage that task a lot closer as well. Unstructured tasks, they inherit properties of their originating context. So this could be something like the priority in which the task is scheduled. I expect that you'll be creating a lot of unstructured tasks, especially when you need to start async work from a non-async context. So for example, maybe in your app you have a button that when you tap it, somewhere down the line, it triggers a network request. Somewhere in there, you'd want to create a task for that network request to run in. Tasks are created pretty easily just using the task initializer, and anything that you put into the closure there will be run asynchronously. Now, when you create a task this way, it returns to you a task handle. And with that task handle, you can check up on a status, like whether it's complete or canceled, and you can also cancel the task as well. And this task handle, when it's returned to you, you can hold on to it to cancel it if needed, but you don't have to. If you let that task handle go by and you don't hold on to it, that's completely okay. The task will still run to completion and it's good to go. Now, this is especially refreshing if, like me, you've been using combine and storing sets of any cancelable all over the place. So let's see this in action, this unstructured task. In our example, we have a view controller with a couple buttons, and each has a button press function here. Our first one, when the fetch report button is pressed, we create an unstructured task in which we can fetch this cow report. You can see that the task is returning a task handle that we're holding onto in our view controller. And we can coincidentally use that task handle to cancel it. Let's say this fetch takes a really long time and our user is frustrated and they cancel it to move on with their day. Well, we can cancel the task entirely with that task handle. And now we're preventing unnecessary background processing. So for scenarios where you need even more control than just unstructured tasks give you, there are also detached tasks. Detached tasks provide the most control, but also come with the most management. And detached tasks, they're nearly identical to unstructured tasks. However, they come with one caveat. They don't inherit any of the properties of their originating context. It's you that gets to provide those. And detached tasks can be created very easily using this task.detach method. And I've found in my usage that detached tasks work really well when you want to kick off some async work, but you don't necessarily care about the result. Maybe this task that you want to run, it's of really low priority, and it's something that doesn't necessarily contribute to the success of your user. So things like analytics, logging, and caching. They're not strictly necessary for your user to get their job done, but they're nice to have. So shared mutable state is a tricky business when you're working with concurrency. And Swift 5.5 bring along actors to alleviate this pain point. But before we jump into actors, I want to remind you of your favorite kind of bugs. And yes, you should have gotten some sort of chill down your spine or goosebumps, because data races, they're just, an unfortunate reality of building concurrent programs. Of course, they occur when two or more pieces of code access and at least one write to some shared bit of memory. And these issues, they're very easy to introduce, but notoriously difficult to track down. In our example here, we're reading and writing to the shared instance of cowherd from both of these concurrently executing tasks. The resulting print statements here could vary between runs, right? One task may run before the other and vice versa. Or both tasks may run simultaneously, and we try and set and read herd name at the same time, and this can put our program to an ill-defined state and even possibly produce a crash. Now, fortunately, Swift can see this pretty early on and issue a compiler error. It's telling us that this instance of cowherd is being captured between these two concurrently running tasks and could lead to potential issues. So in come actors. Actors are a new entity that safely provides shared mutable state to concurrently running tasks. And actors are actually reference types. They're very similar to classes, but they protect their mutable state via two means. The first is isolation. Only the actor itself is allowed to modify its mutable state. Actors also implement a serialization mechanism to ensure that only one task is able to access its mutable state at a time. So let's explore more of what this means through probably my favorite form of development, error-driven development, right? So we'll start by just changing our cowherd class to an actor and see how far that gets us. Unfortunately, we have another error here to deal with. Turns out we're not allowed to do this. We're trying to modify herd from our task, but remember that actors are the only ones that are allowed to modify their mutable state. So let's do just that, right? Let's just brute force this and create a set name method in which we're actually setting the name from inside of the actor. Now, if we try and run this, we're still met with yet another error. The compiler says that this set name method, it should be called with a wait. But if we look up there at the definition of set name, you can see it's not marked with async, so that's kind of curious. So this is actually a feature of the actor's serialization mechanism. Remember that only one task may access the actor's mutable state at a time. And so when we're calling set name here, the actor could be busy with another task. So our function here needs to recognize that the actor may be busy and we should suspend until it's not, and we can do our work then. So let's do just that. Let's mark that as a wait and we're good to go. We can compile this and run. So let's diagram this actor isolation and serialization model out. So first, in the isolated context of an actor, we have synchronous access to everything we need. Remember that our set name function could access that name property synchronously. No need to use wait. Now from the outside of the actor, from our task, we have asynchronous access into that mutable state. And I'm sorry to say, but this is not fully fleshed out just yet. There's also a non-isolated portion of an actor that we'll dig into. So we've added two things to our actor here. The first is this animal type. And you'll see that animal type is defined as a let. It's a constant, right? The second thing here is we've added this function, what does cow say, and which is marked as non-isolated. So when we try and call these things, you can see that we don't need to use a wait. This compiles just fine. So the reason we don't need to use a wait when accessing the animal type is because it's constant. We can't change it. A data race is impossible because there's no write involved. And so we don't have to go through the actor serialization mechanism. The other thing here, the what does the cow say, when we call that, we also don't need to use a wait. This is a feature of that non-isolated marker there. A function that's marked as non-isolated, while it is part of the actor, it doesn't run within the isolated context of the actor. So let's see this as part of the diagram as well. We have our non-isolated context here, in which our immutable properties and our non-isolated functions exist. When accessing that non-isolated portion from the outside, we have synchronous access. We don't need to go through the actor serialization mechanism. From the non-isolated portion of an actor, we have asynchronous access to its isolated portion. It's kind of funny that an actor, it can have a non-isolated portion that still needs to go through its own serialization mechanism to get to that state, but we're safe from data races. So let's look at some more of the details that make actors so cool. And the first is the threading model. It's worth noting that because we're using a wait to suspend our function because the actor could be busy, we're implicitly saying that it should run on the background. There is one exception to that rule though, and that's the main actor, and we'll get to that in a moment. actors, we don't say what thread they should be running on. That's entirely controlled by the system. And like classes, we can create multiple instances of an actor, and each will have its own lightweight serialization mechanism. And actors also work great as more architectural level components, things like logical controllers, managers, and data stores. Any place where you can create an island of data and you really want to make sense of its access model very easily and safely. So like I said, let's touch on the main actor while we're here. The main actor is a concrete implementation of an actor that ships with these new concurrency features. The main actor represents the main thread and comes with this new main actor annotation that we can place on classes, functions, all sorts of things. And as you can expect, when we call into anything marked as main actor, we have to use await because it could be busy, right? So the implication here of this main actor or annotation might not seem obvious, but it's actually amazing. So when you're writing a function that you know has to be run on the main thread, you know that you have to call it from the main thread, right? You have to use that dispatch queue main async to get on the main thread to call that function. And you have to remember to do that all throughout your code, every single place that you call that function. When we mark something with the @main_actor annotation, the language is guaranteeing that it will always run on the main thread. So we can set this once, and it will ensure correct usage everywhere. You don't have to remember, as the developer, to always call this function on the main thread. So knowing when to use dispatch queue main async, it's an entirely solved problem. Yeah. So let's hit some of the key points here. The first being the ergonomics of writing concurrent code. They've been incredibly improved. Function suspension means we don't have to work with any sort of promises or futures or anything synchronously. We just get to pretend that a function's being called, and we can handle the result here just after that. And also using Swift's built-in error handling mechanism, it makes for a really streamlined control flow, right? At times it might feel like you're always pair programming with another developer just by all the issues that the compiler is picking up for you before you even run your code, right? So things like always calling an async function with await. The compiler enforces that. You'll need to remember it. The compiler will make sure you remember that. And also, actors allow us to safely provide shared mutable state to concurrently running tasks and reason about its access very easily. Finally here, local reasoning and scoping. We can poke around a few functions and quickly get a sense of the concurrent nature of our app without a fuss. The lifetime of a task created with async let or a group task is predictable. They already follow the ingrained static scoping semantics and let us focus more on control flow and less on coordination. So a few recommendations before I finish here. So please try and give the do, try, catch mechanism with async functions a chance. I know that coming from the callback world, you may think, I'll just return results here and be able to check into. Don't do that. Please give it a chance. When converting over to use async await, it can be infectious. When you just go into one of your modules and change a function to be async, all of a sudden now you always have to call that function from an async context, and you can see how that bubbles up and outward. So my recommendation is to modernize modules at a time and even create shims for your APIs. So Xcode provides these refactoring tools to create wrappers around your existing callback code, stuff that already works just fine, but you want an async await interface for that. And the bridge between the async await world and the callback completion handler world is via these things called continuations. And Xcode provides this to us really easily. So going through the editor refactor menu, we have these three functions. And for this example, I just chose the last one, add async wrapper. So we went from the above code, or the above function, fetch cow, and Xcode created this, or generated this function below, which just wraps around that fetch cow completion handler based function. And now we have an async throwing interface into our existing code already. So a few more recommendations. First is stop using any sort of thread locks, any sort of OS thread level thing. Please don't use that. Reason being is that you're being abstracted from the OS level thread stuff, right? So any sort of thread modification, you're mucking with stuff that is not managed by you. It's managed by the system, right? So it can have really bad unforeseen consequences. Don't mark every single thing as async. Only mark the things async that really should be asynchronous. Things like accessing user defaults, that doesn't need to be async. And marking every single thing as async could also have some unforeseen poor performance issues. And when it comes to progress updates, you'll notice we didn't have really an example of maybe a 0 to 100, here's how far we are into this asynchronous task. This pattern, Apple recommends delegation to send those updates back, but in my mind, it kind of breaks the illusion. So maybe for the time being, try and stick with combine for that kind of stuff, those kind of stream of updates. And if you do go down this road, be cautious because you'll be building your own solution and you'll be trailblazing a path for the rest of us. And that's all I've got for you today. Thank you so much for listening. And I know this kind of talk will probably leave you with more questions than answers because it opens a whole new world that we're all going to have to get into soon. But I'm happy to answer any questions that you have. So the question was, are there any like recommendations, any habits to get into when interfacing with async code and non-asynchronous code? Is that right? And this is in maybe the context of you're already doing asynchronous calls, but maybe there's some synchronous stuff that don't need to be async, right? It should just work as you hope it would. The async calls, they could suspend, right? But the synchronous ones, they won't, right? You have to do all the work and return before you can proceed on. So it should be kind of the same illusion. And since you're already doing that from an async context, you'll be fine. You're good to go. Yes, okay. So thank you for telling me that. The question, the statement was that task.handle has been deprecated already. So it takes a while to prepare these things right. And over the course of this summer, from beta 1 to, are we on beta 5 of Xcode now? The API for this async await stuff has changed dramatically. At first, we would use async and then have our curly brackets do any async work now, and then it changed to task. And so all the async await stuff that I wrote early on in the summer, well, I have a bunch of compiler warnings to update to the correct usage. So thank you. Don't use task handle, use whatever else it is now. Whatever else it is now. Yes. Okay. Is it a question that you could shout out, or should I really go in?
So now that we're using async await, hoping that lots are crashing, our stack frames.
Ooh, that's a good question about stack frames and crash reports. I know that async functions, when you get into an async context, it actually gets an entire program stack just for that, which can be swapped in and out, and it's much more efficient than switching threads. Sorry, I'm getting deeper into the underlying implementation. The talk about the diving deep into structured concurrency stuff from DubDub described that we only have as many threads as there are cores now, and we're not switching threads. We're switching tasks on those. Tasks are a lot lighter and can be switched around threads a lot easier than threads can be switched in and out of CPUs. So your question was about crash reporting and seeing the stack trace. That's a good question. I have no idea.
Yeah, I feel like it is some deadlocks.
Oh, yes, deadlocks.
So So you can actually, I like to be some up there, but try to come and see it and know what's there.
Yeah. So one of the main places where you could have deadlocks are in actors, right? It's the access model there. I'd have to go back and look at the actor's proposal, but there are two different routes that they're approaching. One is always making forward progress to ensure there are no deadlocks, and I forget the other route that they're considering. But from what I understand, deadlocks should not be so much of an issue, so much of something to be afraid of, because of the method in which actors are created, ensure that you're always making forward progress. Cool. Anything else? Yes.
So you said something about properties and the originating contexts are inherited.
Yeah.
What properties are, what context are we talking about?
Okay, so when you're creating a task and you're already in an async context, so an unstructured task already in an async context, you're going to take on properties like the scheduling priority, which I mentioned, the actor in which that task runs on, which is kind of, you can see that how we're pointing to each other, and yeah. And also, what's the last thing? Task local variables, which is kind of another obscure thing. Basically, you can have variables that are specific to a task, and the way its tree accesses those is kind of special. But those are the kind of things that would be inherited. Cool. All right, I think that's my time. Thank you very much.